Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all students and also our invited speaker. Before we begin our sharing session for today, I've got a couple of announcements. First of all, um, this sharing session will take roughly about 20 to 30 minutes. And after the sharing session is finished, and then I hope all students can ask questions to our invited speakers, any related questions that you may have regarding CFD or maybe his work in general. Okay, so please, I encourage all students to ask questions. Secondly, once the sharing session is ended, we are going to continue with our lecture as usual. So please stay in this session. Do not leave yet. We still have until 4:30 to finish our lecture for today. So I hope after the sharing session is ended, all students will stay on to start our lecture. Okay, so if there is nothing else, I think I'm going to pass over the session to our invited speaker. Before he begins uh, uh, his session or sharing session, I would like to introduce our speaker for today. So I'm pleased to welcome our invited speaker, which is Mr. Azmil bin Datuk Mai Ikram. Um, so a little bit about him. So he's currently an asset manager at Cenergi Sdn. Uh, did I pronounce that correct? Cenergi, yeah? Okay,
Yeah, Synergy, yes.
Cenergi. Okay. And he's basically in the industry of renewable energy, and his current focus is in the Indonesian biogas asset management and operation, as well as business development for other renewable energy power plants in Malaysia. All right, so without further ado, I hand over the session to Mr. Azmir, please.
Assalamualaikum and very good afternoon for everyone. It's 3 p.m. Yes, it's 3 p.m. over here. My name is Azmil. I am a manager in dealing with asset management for renewable energy. So I am doing renewable energy projects with this company called Cenergi, like Dr. Anas here described me just now. So I've been in the industry in power and renewable for 10 years since I left university. I am from Uni 10, University Tenaga National. So I'm a 100% local product. Tak pernah keluar Malaysia. Keluar Malaysia untuk jalan-jalan je. So it's okay. So I am going to present a little bit of my application of CFD in my work. Not this current work, but some previous works, and what it has benefited me up to now. Sebab when I learn CFD, memang pening. It's going to be a really tough subject, I tell you. But once you understand the principles and everything else, which we're going to touch a lot today, eh, you'll see everything. You'll see a lot of things, and your eyes will be open, and you can actually understand problems and solve them better, even without the application of CFD. But you know, the most important thing is the principles of it. So I'm going to share. It's going to be a simple CFD. How to say? Mana dia pergi? It's going to be a simple apa namanya CFD, or I would say presentation. Why is it not in? Yeah. Entire screen, Chrome tab. All right, here it is. So I do hope that you guys can actually see. Yeah, it's going to take some time. Please confirm anyone that can actually see this voice, sebab aku tak masuk dalam. Alright, awesome. So CFD. So kenapa korang ambil CFD ni? I have no idea. Some people say that they want to challenge themselves. Some people say that it's a suicide mission because it's a very, very tough subject. Because there is no CFD is a never-ending iteration of things, but the most important thing is how you understand the principles of it. Uh, so yes, so my contents will be is introduction, what is CFD applications, what it can help you with, my experience. In the end of the day, you can ask me questions, anything.
Azmil,
So
could you please make it full screen, your slide presentation?
yeah, it's already full screen. Tak
Huh?
eh? Tak dapat eh?
How about the others? Student boleh komen tak? Are you seeing a full screen presentation or
No, it's not
just
full screen.
Not a full screen kan?
Sekarang tengah full screen. So semua nampak full screen kan?
Okay, alright.
Okay.
No, still not full screen.
Oh, it's still
Start
not
full
full
screen.
screen.
Still not full screen.
Because mine is already full screen. Siapa yang dah full screen?
Can anyone respond? Are you, who's seeing a full screen presentation of Mr. Azmil's slide? Please,
No
students, could you please comment on the chat box?
Right.
Okay, I think it's okay, Azmil, you can just proceed. But bear in mind, we have several international students, so English, please.
All right, understand. No problem.
Okay. All right, thank you.
Okay. So, CFD is an interesting subject. Okay. So we go with the introduction. The introduction is about the CFD, computational fluid dynamics itself. The first point is you can ask your lecturer about it lah. Academically, these are the things that you'll be seeing, and you'll be seeing this a lot. But application-wise, you almost application-wise basically is just the basic principles, especially on this particular item, the first law of thermodynamics. It's like first law of thermodynamics. It rules everything, almost every application. Previously, when I was my previous work, I was a research engineer for power plants. So I deal with the power, the combustion performance, whereby you have to do simulation of fire inside a boiler. So it's like how do you actually simulate fire? Because fire is a very, very, how to say, intense chemical process whereby it's also turbulent and whatsoever. And you have to determine that. This is where CFD comes into play. So first law of thermodynamics, you'll be touching that a lot. And there's a few others throughout the whole semester. You get familiar with all this. So do ask your lecturer questions. That's the introduction of CFD. The application of CFD, then I will explain it. So there, basically, it's how nature works. It's just fluid going through a particular body. So fluid it doesn't have to mean that it is water. It can be air. It can be a type of even I don't know, up to a certain point. No, it's not solid, but molten solids. Yeah, and also something like from there, this how you understand all this fluid flow, and from there on you can determine the principles, the design of a particular structure, or you can anticipate how or where this type of fluid will end up or accumulate, or even determine what it will bring. Sometimes we need to know, for example, my previous work, the combustion performance. I would like to know where is my heat will be transported. So actually, because the boiler is huge, boiler is huge, like 70 meters. So we need to know, and we need to design, and need to determine where is the most efficient place to extract all this heat for power, for steam generation, and to turn the turbine. So yeah, so this is where CFD comes into place. And CFD, computational fluid dynamics, is just a set of iterations. And I can tell you, it's a very rather young knowledge, I would say. Because if I'm not mistaken, yeah, Dr. Anas can confirm on this. The the simulation of CFD is when computers started to be used for industry purposes, which is in the 1970s. Previously, there were computers before, but it was not that strong. So a lot of people imagine you use all these iterations through hand calculations, so manually. It's very, very tough for them, but they managed to do so. So before CFD, how people evaluate or how people actually understand all this heat mass or fluid transfer basically is pure physical application experiments. For example, wind tunnels for cars, or understand the aerodynamics of cars. So you have to do so. It's time consuming and it's also expensive. So CFD helps you a lot in terms of you save a lot of time because you simulate computers, and computers are getting faster and better throughout these years. And then it is also it will cost less, a lot less. So cars can be cheaper, better cars can be produced, more fuel efficient cars can be produced through the nature of CFD simulation. So application is a lot, almost everything, even medical, and also to determine or understand how your weather gonna work. So aerodynamics, everyone knows that. Formula One, the KLCC building, they use all this to determine because the number one thing that when we talk about CFD is all about for this aerodynamics is actually wind. And sometimes you would like to have the drag in for a particular body, so we have to design it in such a way. Sometimes we have to make it very, very aerodynamic. The coefficient has to be very low because, for example, structures, and when a wind passes by, it creates vibration. So and if at a certain level of vibration, it creates resonance. So if there's resonance up to a certain level, the structure will eventually fail. So we don't want that to happen. So this is where CFD comes into play. It helps. Medical research, blood flows and whatnot. Yeah, I've seen actually one person doing how blood, a simulation of how blood flow can go from this place to another place, and what happens if that particular artery is clogged and whatnot. So it's quite interesting. Military, you can guess it. Power generation is what I actually going to touch on a lot because I am from the power and generation industry. So heat concentration, steam cycle, turbine efficiency, maritime, ships, uh, the sometimes it doesn't have to be just ships, but the oceanography, um, how we deal with certain parts of the ocean. So at this particular time, it's like, oh, the flow most probably is going to be like this. So it's better you avoid this particular path. Instead, you choose the other route. And also geology, we can actually simulate whether forms and up to some point you can determine. Anybody have actually watched Day After Tomorrow? Yeah, you can. There's a lot of basically Day After Tomorrow is a movie back in the early 2000s. It's quite old. And then so there's three big cyclones, I think, and then they use some simulations to that. It's a type of CFD. So that's where how we determine or understand weather patterns, and also it goes all the way to astrology, the path flows of our satellites and planets and whatnot, and the particles and whatnot. So that's the application is for us to determine. So like I mentioned again just now, is for aerodynamics. On the right side, as you can see, is a car. That's a Porsche GT4, if I'm not mistaken. The right, the red or the hot colored
Mr. Azmil,
is
I'm
actually
not sure
where,
we are all
yeah.
seeing your slide actually. The slide is
Uh,
still not moving from the contents.
oh, which content?
I
Context
think the
alamat.
second slide, second page.
So just now I mentioned about applications, yeah. No wonder you guys must be having a you guys must be confused. What am I blabbing about? So yes, application is it ranges from medical all the way up to the macro scale of determining weather patterns. So you can actually understand that CFD is used a lot on almost everywhere. So the most well-known CFD application is for aerodynamics. I think a lot of people of you guys know. On the right side is in GT4. The hot colored is actually where high pressure is. Sometimes it's intended to have high pressure here, so that actually you go through, the wind pushes you down. Reason being is where the wheel is. Wheel needs traction. Wheel needs grip to perform better. So that this is why some cars are designed such a way that certain places you need to have spoilers like such as this, so that they can push you down, push the car down, so that they can have better traction, better control. So in the end of the day, it's better performance. So yeah, and over here is actually heat transfer simulation of a particular body. If I'm not mistaken, this is heat transfer from a microprocessor. These are the processors inside your computer actually. So what goes through and how they cool it off and whatnot. And the next part is so known CFD application. This is still aerodynamics, but this is the Burj Khalifa, if I'm not mistaken. That's the wind resistance to it. So it has to be very, very low wind resistant. If not, you will have problems. The engines have to design it so that to make sure that it can withstand wind. So as you can see here, might not be able to see that much. There's small spots of red or hot colors. So that is where the high pressure is. But most of the time, you can see is almost all of them are blue or green. So it shows that when a wind passes, when a fluid passes through this particular body, you wouldn't have any problem. And this one is actually this small, it's like sketches. It's actually not sketches. It's actually arrows. I don't know whether you can zoom in or not. Let's say, can you guys see? It's actually arrows,
Yes,
right?
boss.
So these are actually arrows, and this is one of the uh, basic electrical appliances that we have in our household, and it's a CFD application to it. It's actually our ceiling fan. So as you can see, the blue is actually the air. I mean, the whole area is the air. This is a room. So this is air. It circulates through this low velocity air, and once it passes through this particular thing, this straight bar is actually the fan. So the velocity picks up, as you can see over here, picks up, and then this is where sometimes certain corners of the room you don't feel air flowing because it's practically we call it dead zone. So the best place to be if you're hot or you need air is underneath the fan. So yeah, even a simple basic ceiling fan can be simulated. This is what I am actually mentioned about. This is the formation of the cloud, as you can see. This is the arrows showing that this is the flow where it's going. Sometimes we can determine that these flows, the wind flows from the moisture and the hot air, the cool air, we can determine whether it's going to be potential thunderstorm or is going to be, you might break the clouds. Yeah, so they are breaking clouds. So so in geology, so you can understand that. This is what the application that our met department is doing, and sometimes it is also presented in the weather channel and whatnot. Some of the videos, if you can see On the right hand side, this is where boiler is. This is a coal-fired furnace, the size of, I think this is the size of around few hundred megawatts. So it's at least 20 to 30 meters in height and 10 meters in width, at least. So it is opposing fire, as you can see. This how to say, the nozzles is actually nozzles, and this red thing is actually a fire. This is where I mentioned just now that how this is what you need to know, and how you need to know as part of my work, where is the best place for me to harness the heat for my steam generation and for me to generate power later on. So the heat flux is where it's over here in the middle. Is pretty known because this is the burner, the nozzle is. And this is supposed to be most of the combustion uh, reaction takes place. So as you can see, our deposition flux. Okay, this is quite interesting. Okay, deposition is where deposits. This is where all the particulates will accumulate. So inside here, there's some flow, there's some fluid flow, and particulates eventually will rest somewhere. So with CFD also, you can apply, you can also determine, because for power plants, too much of a deposit reduces its efficiency in transferring heat from the furnace to the steam pipes, and also eventually to the steam turbine. So it is actually very, very important for us, because sometimes we cannot see with the naked eye, and also how to see inside a furnace when it is operating, because all you see is a very bright fire and it's very hot. So CFD is number one way to go. Previously, I forgot. Previously, CFD is just a supplementary validation to physical tests. Now, CFD, the computer power, and also people have, I mean, the engineering research body have known the assumptions and the coefficients to all this, to their particular type of simulations. They know so much and so well that CFD now is the main test, and physical testing is just a mere validation. So nowadays, people rely more towards the simulation rather than physical testing, because CFD last time people don't like it because it was not so accurate in terms of their results, it because the more iteration you do in your on your equation, the more accurate it'll be. Dr. Anas will actually eventually explain it later, but um, last time computers are not so strong, so they can do only what, few hundreds. Nowadays people can iterate up to like few thousand, 100,000, or even millions. So the more iteration you can do, the smaller your particles can you can determine smaller particles, particle flows and whatnot. So in the long run, it will be almost accurate. Yeah. And also from this CFD, you can create physics engines, and you can actually mimic real life application in. Nowadays people are actually taking all these simulations and whatnot. They're trying to put it into um, VFX, visual effects, games, movies and whatnot. So CFD does play a role. Yeah. So who wants to practice CFD while you're in the workplace? No, actually, not many CFD application in current workplace, in current industry. Not many actually. I am quite lucky to practice it for 2 years in my career. It's either you be in the research, the R&D or consultancy service, or you be in a very large company that has an in-house research. So just like thermodynamics, you won't get it the first time around. Yeah. Who understands thermodynamics first time around? You guys are smart, or you guys are just crazy. You guys are psychopaths. But I couldn't understand my thermodynamics until I did my master's. Uh, truthfully speaking, honestly speaking, because it's once I understood it, everything comes very, very easy. So CFD is the same thing as well. Yeah. After you reach enlightenment of the principles, you can see fluids. You guys should watch Matrix, the movie. So Neo, when he has reached that level of enlightenment, he only sees codes and wire and binaries. Everything is in black and green. Same goes for CFD. It's like after you understand the principle, somehow things moving, the wind moving, you will see actually like this thing come over here and then pass through me and eventually you go to the left or right or up and down. You somehow can understand. You can somehow anticipate fluid flow. Yeah. And this is the picture of the Elon Musk, the Tesla pickup truck. So somebody had a CFD done onto it, and surprisingly, it told the simulation told us, explains to us that it is very, very aerodynamic, even though it's boxy. Yeah. So my experience with CFD, this is what I did previously. Cannot show you much, but yeah, we did a combustor, a cyclone combustor that mimics a utility scale furnace. So on the left side, as you can see, this is how the flow of a particulate that goes through the wall. What we want to have is something like this. It's a tangential flow. Yeah. And then this on the right hand side is actually where the velocity is. As you can see, it's cyclonic, whereby velocity increases towards the outer region and it is more stagnant on the middle region. Yeah. So for me is I was involved in a coal plus biomass co-firing. So we had to research on how the particulates, how the combustion performance will be, because coal, it goes on with micron scale. You pulverize coal into micron scale, like 200 microns, 50 microns up to that point. It is very, very soft. It's softer than your normal flour, actually. Imagine you mix it with biomass. Biomass, the problem here is when you pulverize it or you cut it, the smallest particle you can is actually 1 mm. It's not small enough. For pulverized coal furnace, that is considered as big. So we need to determine the combustion performance, the trajectory, the combustion, the heat transfer, and a lot of others. So it is what I learned is throughout my whole job during that time. I had to apply CFD. I was still a little bit blur, and it took me 6 months to actually properly master it. Focus on CFD simulation and research. Just doing that, 6 months, just doing that, creating that particular how to say box, the body of simulation inside Gambit, and then you have to open Fluent to do the simulation. All of those you'll be doing it later on. So from there we need to determine. And I've been playing around with this day in, day out for 7 days. Yeah, I do work on weekends at times, and to actually understand how my combustor, the cyclone combustor, actually works. So as you can see over here, some not so bright lights, okay, but hot colored compared to the bottom. This is actually temperature, if I'm not mistaken. Yeah, temperature. Some spots. This shows that the flow of the flow of the flue gas is cyclonic. So cyclonic, and it goes up. It goes here and then here and then here. and then eventually exit. So this is the main reason. So from there is CFD shows that okay, from this we can somehow assume, because we cannot see physically inside cyclone combustor, somehow assume that the hot patches are where the hot flue gas and fire would be. And this is where the velocity is, as you can see, because this is a 2-day simulation of CFD. Is hot over here. I won't say hot colored, yes, and it's cool over here because, as you can see, let us focus here. So as you can see over here is 4.5 meters per second. It's fast towards into the page, and the blue color is 6, between 4.5 to 6, going out of the page, as you can see, out of the screen, sorry. So it shows here again that it is running in circles. So one has to go in, one has to go out. So eventually it goes all the way in a cyclonic manner. So yeah, next is another year of trial and error, and finally I could understand actually how my from that research and simulation I can determine saying that mixing biomass, in this case palm oil, with coal is technically feasible. Yeah, it's a two-year thing. So as you can see here, I hope people don't ask me so much technical questions after this because I will have a hard time explaining it. So from there, I can create a graph from the software determining the combustion performance. From this, you can see the O2 goes down. It means the oxygen is utilized for combustion, and then it's fuel presence. So as you can see, there are lines over here. These are according to sectors of the cyclone combustor. So this is where the fuel comes in, and then straight away is devolatilized and it's burned off. So there's some small peaks here and there. So this is to show that, okay, so either the simulation is not that correct, or there is a loss of ignition towards the end, meaning by it's unburned fuel, and CO presence in combustor. Okay, why CO presence and oxygen is almost the same? Because before, you know, when you burn something, the result is CO2 plus water, right? It doesn't have to be like that eventually, because the first step is actually CO. And then there'll be like a lot of other chemical reactions along the way, eventually end up with CO2 and H2O. So it is to show that this particular simulation is to show that I have enough oxygen supply or air supply so that all of the CO converted into CO2. And also this is to determine, or this is to provide pointers saying that CO2 depletes mean all of the oxygen content is properly converted to CO2, meaning by the fuel over here is fully utilized. If CO is high, that means there'll be problems with the fuel. Fuel is not fully burned. At the end of the day, it's not more efficient. So that from all these observations and whatnot, we can somehow determine whether our plant is efficient or whether we have any problems with the plant, and also we can further understand, say, okay, next, what can we do to improve the plant? All right, so that's CFD particularly for you. So I apply understanding of fluid flow in my next previous, my previous, sorry, and my current job. And basically my previous job was is a coal consultant for TNB fuel, and I've been to all the coal power plants in Malaysia, there's one in Johor, KL. KL is not so entirely in KL. It's in Kapar, which is north of Klang, and there's one in Manjung, Perak. Yeah. So these power plants over here, I've seen it, and I can actually understand from their drawings. I can say, okay, there is a possibility there might be fire touching over here. Do you have enough oxygen? Is the burner running or not? And from there, we can determine possible deposition from selected areas, and also scorch marks on furnace walls and whatnot. So these are very important to power plant, because they need to run optimally. Because if not, they'll lose money because of not being efficient. A reduction of efficiency and heat rate by 1 to 2% will cost them millions of dollars. And then understanding identification of the heat flow, gas flow, particulate, and possible deposition, like I mentioned earlier just now. And also currently, and understanding fluid flow in biogas digesters. This is what I'm doing currently. My company, Cenergi, is one of the pioneers in biogas in Malaysia, and we are one of the big players. We have 7 biogas power plants, and we are building a few more. So we have this thing called digesters. Digester is like body of, it's like our stomach. So inside it, there's food and nutrient. So we take the methane from the excreted by the bacteria. So from here, what is the role of CFD is need to determine the flow of this wastewater and bacteria. They need to be as turbulent as they can, so that the mixture is very good, so that they can be more efficient producing biogas. So there has to be fluid, means food supply by general biogas. So basically, that is my experience with CFD. Not very extensive, I would say, but it has helped me to determine and understand things better, and up to a minute level, I would say. So from there on, I can say that CFD, even though it's a hard thing, but once you understand it, it'll be easy. Principally, yeah, principally. Thank you. So I end my presentation. I hope you guys have some questions related to CFD or my career, or how you can go through it. I mean, CFD in your future jobs.
Students, now is the best time to ask very hard questions to Mr. Ikram. Come on, jangan bagi dia malu.
Maybe you
Question,
have
please,
something in the
guys.
chat. Okay, tak ada. You guys can type if you guys are shy. No problem.
At least 1 or 2 questions, please.
Okay, even if not, then I can ask questions to you guys.
Trial version.
Well, okay. Did somebody
Trial
say
version.
something? No, okay. Trial version.
I'm hearing trial version. I have no idea what it is.
Trial version.
Trial version. I think no idea. I think this Webex punya thing is a trial version. Yeah.
Okay,
So
I think Mr. Azmil, you got a question. Yes, please.
yeah, are you guys gonna practice or apply this CFD that you guys gonna learn in the industry? And do you have any idea where you guys going to apply it? I mean, in terms of work or job. Okay, hi, Mrs.
We got a question
Siu
from
Chi
Siu.
Fung.
Siu,
Yeah.
please continue.
So yes, that was my question just now. It's like, or you intend to continue this in the academics? Pun no problem. So I would like to hear some of your answers. Where are you guys taking this? Oh, there's a question. The question just now, I do hope one of you guys can actually answer, because I would like to know. Because for me is I have no idea CFD will bring me until I landed a job as a research engineer. Okay, wassalam. Waalaikumsalam. The first question, throughout the application of CFD, which phase of it did you feel most challenging? Is it the designing, analyzing, validating? Can I say all? um, okay, different difficulties, different reason of the different types of challenges. Designing part is purely technical, so you have to really understand what you're going to design. So in my case is I have to design the cyclone combustor, so I have to really understand the dimensions. I have to really understand the software that I'm doing, all this. So it took me a few months, yeah, to play around with it. Okay, analyzing is another thing. Computers are not that strong last time. So it's simulation. You play with all the assumptions and whatnot, and then you had at the end of the day, Google is your best friend. Google and YouTube is your best friend. So you can just, yeah, if you have no idea how to make smoke or how to simulate fire in an open space, you can just Google it, because my friend did and he found answers. People help him. There's forums actually. Validation. Yeah, validation of my simulation I had to do in a physical experiment. Waalaikumsalam, Mama Ismail. Why is the biggest challenge in doing CFD in large scale project? In your previous job scope? Large scale. Practically, if for CFD, besar, big or small, everything is the same. At the end of the day, is how you understand fully the coefficients or the scenario that you're going to simulate. For example, if you're going to simulate inside a furnace, you have to fully understand what is inside the furnace. You have to understand the parameters that is going to be used, uh, boundaries. So that is very, very important. Um, so, and also you have to understand also the principles of from there before you actually simulate. You can somehow determine or create a hypothesis saying that, okay, this situation, what will happen? And things like that. And then the most challenging, I would say the large scale part, if you are referring large scale, is actually on the analysis part, whereby setting up the parameters. You have to be very, very detailed. But academic wise, you don't have to think we can do something simplistic. But if you play with um, industrial, I don't think you need academic level softwares. You might need to jump into more complicated softwares, or even you have to create your own software or formula. For example, Fortrans. You have to like do programming so that you can create a simulation. Any other questions?
What else? Okay, I think that's good.
Okay.
Okay, so on behalf of our class and UNIMED, I would like to thank Mr. Azmil for your extensive sharing session today. Okay, we got one last question, Mr. Azmil. Does Malaysia have any certification bodies for CFD?
Not that I know of, actually. Certification bodies, there must be, definitely there'll be, because people, whenever people do training, they must be certified and competent. But like, for example, like certification, I think we can start with IEM, Institute of Engineers Malaysia. So you can start there. From there, you can look. because I did not go very extensive into CFD like I mentioned earlier. So to the point of the certification, but definitely worldwide there are peer-to-peer programs and validation and also discussion forums. Some of it is official, some of it is unofficial. You can just Google and search of all these forums to understand your problems. They can help you. These guys are helpful.
Okay,
All
hopefully
right.
that answers Ashik's question. So again, thank you so much, Mr. Azmil, for your time and for your insights into CFD. I
No
hope
problem.
this sharing session open the minds and also hopefully encourage students to challenge themselves basically, as Mr. Azmil said. It's quite challenging, but after you understand the concept, the fundamentals, the the rewards is quite fulfilling. I hope we all can take that from this talk.
Very,
So
very
again,
true.
Mr. Azmil, thank you so much. We hope to see you again soon, hopefully. All right.
Okay.
So thank you so much, Mr. Azmil.
All right. Thank you.
Okay, for the rest of the class, hopefully you can stay. We are going to start our lecture after Mr. Azmil left. Um,
Okay.
okay, so